Hello, I am Dr. Zenya Worth, and in this video, we will be discussing applications of integration. We will discuss finding volumes by integration using both the parallel cross-sections and the solids of revolutions method, and we will discuss finding centroids by integration, which is something that will be very useful to you in future courses. First, let's talk about finding a volume by integration. There are two ways to do this, and it depends on the area and volume that you have. The first way is using what's called the parallel cross-sections relationship. If any object has a cross-sectional area A of x that varies continuously with x, then we can find the volume by integration by taking the integral of this area over d of x from two limits a to b. And the area times the length will give you the volume, and you integrate over your appropriate limits. Solids of revolution are created by revolving some region bounded by a function f of x around the axis. So you have an x-axis or a y-axis, and you revolve some relationship, linear, quadratic, some function around an axis. And by revolving, you actually create a volume of material. And you can find that volume by the integration from limits a to b of pi times f of x squared dx. So let's start with the parallel cross-sections method. This is something that we actually use and see every day with a lot of common shapes that we find the volume of, but we can actually describe them by integration as well. Shapes such as cylinders, rectangular prisms, and square pyramids all have parallel cross-sections that vary continuously with x. Let's look at a cylinder over here on the left. So there is a cross-section of a cylinder that is described as a circle. And that circle, if you integrate that circle or the area of that circle over the height of the cylinder, you get the volume of the cylinder. The same thing for a cube or a rectangular prism. It has some cross-section described by the length and width of a square, and you integrate that area over the height of the cube or the rectangular prism to find the volume of that prism. We can also use this relationship for some shape that's a little more complex, like in this case, a square pyramid. The actual area of the pyramid is a square, but that square changes in length. The sides of the square change in length as you move up the pyramid until it reaches the top of the pyramid. But since this is a cross-section that varies with x, we can integrate in the same way to find the volume. So let's see how we do that for each of these shapes. For the cylinder, it's pretty friendly. We have the area described as pi r squared, which is the area of a circle, and we integrate that from 0 to h dx, and we find that the volume of a cylinder is in fact pi r squared h. I can do the same thing for my rectangular prism. The area or the cross-sectional area of this is L times W, the length times width, and we integrate that over the height of the prism to find that the volume of a rectangular prism is indeed length times width times height. It gets a little more challenging when we talk about our square pyramid, because in this case, the side lengths of the square that make up the base of the pyramid change with height. So in this case, we don't have an area that is constant with x. This area is actually changing. So we need to describe the side lengths of this square in terms of the variables that are either constant, such as height, or the base length of the square, which is r and r, and x, because it is changing with x. To do this, we set up a series of similar triangles here, where we can describe the length of the side of the square at any moment from 0 to h, based on the variables r and h and x. So we set up our similar triangles, and we discover that the actual length of a side is r over h times h minus x, which means that the area of the square is s squared, the area of the length squared, which is actually r squared divided by h squared times h minus x squared. So in this case, we have our variable x, it's part of our area function, and we integrate this from, again, 0 to h, or the height of the square pyramid. And we find that the area of a square pyramid is actually 1/3 r squared h. While these are somewhat friendly, easier examples to internalize, you can extend this method for any shape that has a cross-sectional area that varies with x. The next aspect of finding a volume is using a solid of revolution. A cone is a great example of a solid of revolution. It is created by revolving a linear relationship f of x around the x-axis, where r describes the radius of the cone and h describes the height of the cone. So in this case, we have a relationship y is equal to r over hx, where this is a linear line with a slope r over h. And then we're actually taking this line here, and then we're revolving it around the x-axis. So we're bringing it around in 3D and revolving it. And by revolving this line around the x-axis, we actually develop a shaded area that is a cone that has a height h and a radius r. And we can use integration to then determine the volume of that cone. We take the integral from 0 to h, the height, which is also the variable that's changing in the x direction. Pi times r over hx squared dx gives you the volume of the cone, where r over hx is actually your function f of x. So you square that dx, and you find, after simplifying and applying your limits of integration, that the volume of a cone is indeed 1/3 pi r squared h. A second application for integration is finding the centroid of a region, and this can be very useful if you don't have a shape that has a nice, easy centroid formula. The centroid is defined as the center of mass of an object that has a uniform density. This is hugely applicable in structural analysis because you need to find the weight of a beam, the weight of an object, and to find the weight, you need to know where the center of mass is. If we define an area A that can be expressed by some function f of x and is bounded by limits a and b, then we can find the centroid of that area or the center of mass of that object, assuming it has a uniform density, as the x-coordinate of the centroid is 1 divided by area, the integral from a to b of x times f of x dx. And the y-coordinate of your centroid is 1 over a, the integral from a to b of 1/2 f of x squared dx. And this is sort of described by this figure here, where you have some sort of curve, f of x, that has some sort of function. And taking the limit of that curve from a to b actually creates an area here. So you're taking the area under this curve, bounded by f of x on top and the x-axis on the bottom. And you can find the centroid or the center of mass of this by following these relationships. Sometimes your area can become more complex. What if it's bounded not by the x-axis, but by two functions? So f of x on top, g of x on the bottom. We can use what we know of both of those functions to determine the centroid. If f of x bounds the area from above, like in this shape, we have a parabola here that bounds an area from above, and g of x is a shape that bounds, or is a function that bounds the shape from below, we end up having a shaded area in here. And then that area will also have a centroid, x bar, y bar. To find that centroid, x bar is 1 over a, the integral from a to b. So you still have your integration limits, and these integration limits are defined where these two curves intersect. So those are going to be, a is going to be the left-hand side intersection, and b is the right-hand side. And in this case, x bar, or the x-coordinate of your centroid, is the integral from a to b of x times f of x minus g of x dx. And the y-coordinate of your centroid is, again, 1 over a, integral from a to b of 1/2 fx squared minus gx squared dx. So the formula gets a little more complicated if you have two functions involved, but the process is essentially the same. Let's do an example with a shape that we've seen before that we know from general geometry. Find the location of the centroid of a quarter disk with a radius of 1, and the actual function that describes this quarter disk here, which is the quarter of a circle. The function that describes this is f of x is square root of r squared minus x squared. And here we have a figure here. We need to determine what the coordinates or what the number of the centroid is. Like, where is this on the x-axis? Where is this on the y-axis? If the radius of my quarter disk or my quarter of a circle is 1 in the x direction and 1 in the y direction. So first we need to find the area of the shape. Since I know that this is half of the area or a quarter of the area of a circle, I know that the area of a quarter disk is 1 over 4 pi r squared. The limits of integration also need to define. And in this case, they're going to be 0 to r generically, in both directions because this shape is symmetrical. The y-axis and the x-axis is perfectly symmetrical. So we plug in what we know. We have f of x, which is the description of the function from here to here. So what that function actually looks like if we were to graph it. And we have our area, and we have our integration limits 0 and r. So to find the x-coordinate of the centroid, we apply our formula here. The area is 1/4 times pi r squared. If we put 1 over the area, that becomes 4 over pi r squared. We invert that. The integral from 0 to r are integration limits of x times the square root of r squared minus x squared dx. We apply the limits of integration, we solve the integral, and we find that the actual coordinate of the centroid is generically 4 times r over 3 pi, but since r is equal to 1, it is 4 over 3 pi. We do the same thing for the y-coordinate of the centroid, except our formula is slightly different here. 1 over a is the same, but now we have 1/2 times f of x squared dx is our function. We do the same analysis, and we determine that the actual coordinate, y-coordinate of the centroid is 4r over 3 pi, which is the same as the x-coordinate, which, since the shape is symmetrical, is something that you could have assumed instead of having to prove, but we can go ahead and prove it, that's fine. And you find that because r is equal to 1, the y-coordinate is 4 over 3 pi again. So in this case, these values for x bar and y bar are 4 over 3 pi and 4 over 3 pi. I encourage you now to practice what you've learned by applying the second application of integration. Prove to me that the x-coordinate of the centroid of a triangle is b over 3. This is something you'll be using in statics, mechanics of materials, a lot of classes where we see triangular distributions of loads and things like that. It's good to know the centroid of the triangle. So you have a triangle here, a right triangle. On the x-axis, the bounds are 0 to b. On the y-axis, the bounds are 0 to h. So your integration limits in the x direction are 0 to b. And you have a function that describes the hypotenuse of the triangle. So the x and y coordinates of the triangle are straight lines that have no slope. But the hypotenuse is a function that's actually described as h minus h over b times x. So knowing that you know the function, you know the limits of integration in the x direction, prove to me that the x-coordinate of a centroid is x bar is equal to b over 3. I hope you find this information useful in your class.